So imagine this. You are exactly, I don't know, 10 minutes away from a massive live show.
Oh, stressful already.
Right. The venue is totally packed, the band is pacing around backstage, and your main mixing computer just crashes hard. Like black screen. Nothing.
That is literally the audio engineer's ultimate nightmare.
It really is. Normally, you'd be in full-on panic mode, you know? You'd be frantically searching for a backup laptop, trying to download a 2 GB driver package over some spotty venue Wi-Fi.
Yeah, and just praying that the firmware versions perfectly match your console.
Exactly.
Yeah.
But what if, instead of all that chaos, you just borrowed, say, the drummer's personal laptop, opened a generic Google Chrome window, and suddenly 32 physical faders just sprang to life under your fingers?
I mean, no drivers.
For drivers.
No complex installations.
Zero software.
It sounds completely impossible, honestly, especially if you're used to the traditional bottlenecks of live sound networking. Like, we expect heavy industrial permanence in this field.
We really do.
We expect an entire ecosystem of, firmware updates and proprietary cables because the job of routing hundreds of audio channels in real time is just inherently complex.
Right, but that paradigm is getting flipped completely on its head today.
Ah.
So welcome to the Deep Dive. Our mission for you today is to demystify how the zero-install miracle actually works.
We're looking at the setup and the, quite frankly, insane flexibility of the dMix 128 Live Control Fader controller.
Yeah, and on the table today, we've got a highly detailed set of visual interface screenshots, and we're pulling straight from the official Violet audio manual to guide us through this. Okay, let's unpack this. How on earth do you get a massive, tactile, physical mixing desk to run without installing a single piece of software on the computer controlling it?
Well, it really all comes down to leveraging the modern web browser in ways it was never originally designed for.
Right.
Before we even touch a physical fader, we have to understand the invisible bridge connecting your hardware to the actual mix. I mean, the entire dMix 128 Live Control app isn't a program you install. It is essentially just a single local HTML file. You open this file in Google Chrome or Microsoft Edge, and you're just in.
Wait, let's pause there for a second. Because looking at the manual specs here, it specifically calls out that Safari and Firefox are out of bounds. Like, they won't work.
Yeah, that's correct.
So if it's just a web page, why does the browser actually matter so much?
Because it relies heavily on a really specific underlying protocol called Web MIDI.
Web MIDI, okay.
Yeah, so historically, web browsers were heavily sandboxed, right? They were walled off from your computer's physical hardware for obvious security reasons.
Right, you wouldn't want some random website being able to secretly turn on your microphone or hijack your keyboard.
Exactly. But Web MIDI is a specialized API that creates a secure direct door specifically for musical data.
Oh, interesting.
Yeah, it allows the browser to speak directly to your physical MIDI hardware using the MCU or Mackie Control Protocol. Chrome and Edge built robust native support for Web MIDI directly into their architecture.
Ah, I see.
But Safari and Firefox, however, they've kind of kept that door closed due to differing security philosophies.
Okay, so the browser is using Web MIDI to talk to the physical faders sitting on the desk right in front of you.
Right.
But that's really only half the equation, right? How does this browser window talk to the actual dMix 128 console? Because that thing might be sitting 50 feet away in a server rack or strapped to the side of the stage.
Yeah, that is where the network protocol comes in. While the browser uses Web MIDI to talk to the faders, it uses something called WebSockets on port 80 to talk to the console over your local area network.
WebSockets. I know standard web traffic, like if I go to a news site,
Yeah.
that's based on HTTP.
Yes, exactly.
So how is a WebSocket different from that? Why not just use normal web requests?
Well, traditional web traffic is very transactional. It's
Yeah.
essentially a game of ask and receive.
Okay.
You click a link, your browser asks the server for the page, the server sends the data, and then the connection just closes.
So if you tried to mix a live show like that, there would be massive latency.
Oh, huge latency.
Right, I push the lead vocal fader up, the browser would have to formally ask the console to turn it up, and I'd be sitting there waiting half a second to hear the volume actually change.
Exactly, which is totally useless in a live environment. A split-second feedback loop can completely ruin a show.
Right.
WebSockets change the game by opening a persistent, continuous pipe. Instead of ask and receive, you're laying down a multi-lane digital highway where the data cars never have to stop at a toll booth.
They just stream back and forth instantly.
Exactly.
Which really explains the actual setup process in the manual. Because to connect this whole thing, it says you literally just type the console's IP address into the top bar of this web page and hit the connect button.
Yeah, it's that simple.
And a little status dot turns green, and instantly the app just requests the full state of the desk.
Hmm.
Every fader, every mute, every EQ curve snaps into place on your screen. It's like a magic trick.
It really is. And if we connect this to the bigger picture, think about the massive reduction in friction this creates for you. You don't have to worry about whether you're running Mac or Windows. You don't have to worry if your recent OS update broke your audio drivers.
Right.
You literally grab any machine with Chrome, type in an IP address, and the console hands you the keys to the mix.
That's incredible. So we've essentially tricked the browser into being our console brain using web MIDI and WebSockets.
Yeah, basically, yeah.
But a brain needs hands, right? If I'm a live engineer, I do not want to click a mouse to mix a 12-piece band.
No, you could go crazy.
I need to know how this digital setup maps to the actual physical faders under my fingers. The manual mentions scaling this up to 32 faders. How do we actually build that physical canvas?
We do that through the MIDI button mapping and the MCU setup dialog, which are right within the HTML app.
Okay.
The system is designed to support up to 4 Mackie Control Universal, or MCU, units.
Which is an industry standard communication protocol, right?
Exactly, which is why we can use these generic control surfaces. And each standard MCU unit gives you a bank of 8 physical faders.
So let me do the quick math here. 4 units connected together times 8 faders each. That gives you that massive 32 fader layout across your desk.
Spot on. And the mapping process itself is incredibly visual. You just assign each physical unit to a digital surface in the app's grid.
The surface, okay.
Yeah. So surface 1 is told to control channels 1 through 8, plus your main master fader.
Makes sense.
Then you tell surface 2 to handle channels 9 through 16. Surface 3 takes 17 to 24. And surface 4 wraps it up with 25 to 32.
Got it. And I see a note here in the manual about setting a fader strip count. What's that about?
Yes, that is a vital step. You have to explicitly tell the software your total physical width.
Why is that so important?
Because if you have all 4 surfaces plugged in, you set the fader strip count to 32. But if you only brought 2 surfaces to a smaller gig, you have to set it to 16.
Oh, okay.
The software needs to know exactly how wide your physical setup is, so it understands how to bank the channels when you inevitably need to scroll over to adjust, say, channel 33 and beyond.
Right, because if it thinks you only have 8 faders, but you actually have 32, banking to the next layer will just throw your entire layout into total chaos.
Exactly. It would be unmanageable.
Okay, now I'm putting myself in the shoes of an engineer during a really chaotic festival changeover.
Oh boy.
You know the vibe. You've got band swapping gear, cables are everywhere, the drummer is aggressively hitting the kick drum while I'm trying to think.
Always.
Right. So what happens if I mess up that mapping grid in the app? Like, say I accidentally tell Surface 1 and Surface 2 to both listen to the exact same physical piece of hardware. Does the whole browser crash? Do the faders just fight each other?
The developers actually anticipated that exact sleep-deprived scenario.
Oh, thank goodness.
The software features a built-in duplicate port guard.
Duplicate port guard. How does that actually work under the hood?
So when you plug in a USB MIDI device, your computer gives it a unique identifier. The problem is, to human eyes, looking at a little drop-down menu, 2 identical Mackie controllers might just show up as USB audio device 1 and USB audio device 2.
Oh yeah, it's incredibly easy to click the wrong one.
Right. But because the browser enumerates, or basically catalogs, the unique hardware IDs when the page loads, the duplicate port guard actively monitors your assignments.
Okay.
So if you try to assign port A to Surface 2 when it's already assigned to Surface 1, the software simply blocks the action.
Wow.
Yeah, it physically prevents the MIDI crosstalk.
That is brilliant. It literally saves you from your own mistakes when you're rushing.
Exactly.
Though, reading the fine print here in the manual, there is a specific order of operations to make sure that enumeration actually happens, right?
There is, yeah. You must connect your control surfaces via USB before you load the HTML page. Before, yes. The browser only takes roll call of connected devices the exact moment it launches.
Oh, I see.
If you open the web page and then plug in your 32 fader board, the browser won't even see it. You'd have to refresh the page to force it to look for new hardware.
Makes total sense. Plug in the heavy lifting first, then open the magic window. So now that our hands are attached, properly routed, and protected from our own errors, let's talk about what we're actually driving. Let's look at the channel strip itself, because comparing the screenshots to the manual, this physical interface is incredibly dense.
It is really dense, but everything serves a direct purpose. I mean, the main mixer view on the screen is designed to perfectly mirror the physical desk.
Okay.
The level fader, the mute button, the solo button, they all talk to each other instantly over those WebSockets we discuss.
So if I move a physical fader, the virtual one glides with it.
Right, and if you click a mute on the screen with your mouse, the physical rubber button on your board lights up red.
But the real powerhouse here seems to be the V-pots. These are the rotary encoders located right above the faders on each channel strip.
Yes, the V-pots are crucial.
And for anyone who isn't, deep into audio hardware, an encoder is very different from a standard volume knob, right?
Totally different.
Like an old stereo knob physically stops when you turn it all the way down or all the way up, but an encoder can spin infinitely in either direction.
Exactly. And because an encoder doesn't have a fixed physical position, it can represent literally any value you tell it to.
Right.
And the dMix 128 app takes full advantage of that flexibility. In the center panel of your physical controller, there are knob mode buttons: pan, gain, HPF for your high-pass filter, and LPF for your low-pass filter.
Okay.
The exact moment you press one of those mode buttons, every single V-pot across your entire 32-channel board instantly changes its function.
It's like a sonic Swiss Army knife.
Yeah.
It's not just a pan knob. It completely shapeshifts depending on what you need in that exact second.
Yeah.
And this is where the manual reveals some amazing hidden shortcuts. Because these V-pods aren't just knobs you twist, right?
Yeah.
They're also buttons you can physically press down.
That push-button functionality is how you gain serious speed during a live show.
Give me an example.
So, let's say you are setting up a drum kit. You are in gain mode, turning the V-pot to adjust the input level of the overhead microphones.
Okay.
Those are condenser mics, which means they require external power, right? 48-volt phantom power to actually capture sound. Normally, you'd have to dig into some digital menu on a screen to turn that on.
Which takes your attention completely away from the stage.
Precisely. But here, if you are in gain mode, you simply tap the V-pot down like a button, and it instantly activates phantom power for that specific channel.
That is huge for a quick line jack.
Hmm.
And the flexibility continues with the filters, too. The manual notes that if you are in HPF or LPF mode, twisting the knob obviously sweeps the frequency of the filter.
Right.
But if you tap the V-pot, it steps through different filter slopes, changing how aggressively it cuts the low or high frequencies.
Yeah, and if you press and hold the V-pot for 2 seconds, it acts as a hard bypass, completely toggling the filter on or off.
That really keeps your hands anchored on the hardware.
It does. But there is one more encoder we have to discuss, which is arguably the smartest integration of the whole system, the touch and turn encoder.
Now, I have to admit, when I first read about this in the source material, I couldn't really wrap my head around the mechanics of it.
It's a bit abstract at first.
The manual says it's a dedicated knob that follows whatever you click on the digital GUI. But if I'm clicking a digital screen with a mouse, how does a physical piece of plastic know what I'm looking at?
It works through a really clever exchange of parameter IDs.
Okay.
So when you click an element on the HTML interface, say the frequency band of a parametric EQ, the browser registers the unique ID of that specific parameter.
Right.
It immediately assigns that ID to the touch and turn encoder on your physical board. But it goes a step further. The software sends data back to the physical board to illuminate the LED ring surrounding that specific encoder.
So it's a two-way street.
Exactly. The LED ring will physically change its color to match the color of the EQ band on your screen, and the lights will jump to reflect the current value of that parameter. You get immediate tactile control with physical visual confirmation. It perfectly bridges the gap between the glass screen and the real world.
That is incredibly slick.
Yeah.
But let's push this system a little harder. Because controlling individual microphone channels with V-pots is great for a straightforward corporate gig. But live music is rarely straightforward.
Oh, never.
We have to manage complex groups of instruments, feed subwoofers, and build intricate monitor mixes for the musicians on stage. How does this zero-install controller handle really complex routing?
This is where we look at the master layer buttons and a feature called Sends On Fader.
Okay.
On your center control panel, you have buttons labeled SUB, AUX, DCA, and MTX. Pressing one of these doesn't just select a single master volume fader. It commands the software to swap your entire physical fader bank.
Wait, so if I have 32 faders and I hit the SUB button, suddenly all 32 faders stop controlling individual microphones and start controlling my subgroup masters.
Yes, your entire physical canvas basically adapts to the routing layer you want to manage.
That's wild.
But the real stress test for an engineer is mixing monitors. That requires sending totally different amounts of each instrument to different speakers on stage.
Right, like the lead singer wants more of their own vocal and less guitars, while the drummer wants mostly bass and kick drum.
Exactly. So to do that, you select the AUX or FX tabs, which engages sends on fader.
Sends on fader.
Yeah. The moment you do this, your physical faders no longer control the main volume going out to the audience. Instead, they transform into send levels.
Okay.
Fader 1 is now dictating how much of channel 1 is being routed into the specific monitor mix you've selected.
Okay, let me put my anxious engineer hat back on for a second.
Sure.
Because this sounds slightly terrifying. If I hit a button and my faders suddenly stop controlling the main house volume, wouldn't I get totally disoriented?
It's a valid concern.
Right. If I look down at my board, a fader is just a fader. How do I know I'm not accidentally tanking the lead vocal in the main mix when I think I'm just turning him down in the drummer's monitor?
Well, disorientation is the absolute enemy of a good mix. A mistake like that can totally ruin a performance. What's fascinating here is how the software solves this psychological problem with a single mechanical feature called the Follow Me button.
Follow me, like a digital tether between the board and the screen.
That's a perfect way to describe it. When the Follow Me button is active, the digital GUI tracks your physical actions aggressively.
Aggressively?
Yes. If you enter Sends on Fader mode on the physical board to adjust the drummer's monitor, the HTML web page automatically forces the screen to switch to the exact matching send page.
Oh, wow.
The visual feedback on your monitor locks on to the physical state of your surface. You always have massive color-coded visual context for what those plastic faders are currently doing. The software just refuses to let you lose your place.
That visual confirmation is everything. I feel like it takes all the anxiety out of complex routing.
It really does.
So we've seen the default layouts, we've seen the shape-shifting VPOTs, the routing tethers. They are incredibly well thought out. But ultimate flexibility really means making the board work exactly how you want it to work.
Absolutely.
Because every single audio engineer has their own weird, highly specific workflow quirks.
And the dMix 128 Live Control app accommodates those quirks beautifully through a feature called the AMAP dialog.
Okay.
This isn't just about deciding which channel goes to which fader. This is about fundamentally rewriting the brain of the control surface.
Here's where it gets really interesting.
Yeah.
Because looking at the source manual, it says you can map any physical controller button to almost anything.
Pretty much, yeah.
We're talking basic stuff like mutes or
Yeah.
transport controls like play and stop.
Yeah.
But incredibly, it says you can map physical buttons to trigger GUI key commands. How does that even work?
Well, the HTML app was built with a comprehensive suite of standard QWERTY keyboard shortcuts to speed up mouse and keyboard users.
Okay.
For instance, hitting the Y key on your computer opens the parametric EQ. Hitting T opens the compressor page. Hitting Q jumps you back to the main overview screen.
Okay.
What the MAP dialog allows you to do is take those computer keyboard commands and bind them directly to the generic physical buttons on your Mackie controller.
So let's say I have a button on my physical MCU unit that I literally never touch.
Right.
I can dive into the MAP dialog and tell the software, hey, whenever I press this specific physical button, pretend I just hit Y on my laptop keyboard and instantly open up the EQ screen for whatever channel I have selected.
Exactly. You are essentially designing a bespoke interface. You are taking a generic controller and molding it to your exact neural pathways.
And the payoff for spending the time to build that custom layout is massive, because the manual says you can export that entire MAP configuration as a JSON file.
Yes, JavaScript object notation. It's a standard, incredibly lightweight data interchange format.
Nice.
It saves all your custom routing, every shortcut you mapped, and every preference into a tiny little text file.
We are moving from a world where massive physical consoles dictate your workflow to a world where a 10 kilobyte text file completely commands thousands of dollars of hardware.
It's wild to think about.
It's like packing your highly personalized, perfectly dialed-in muscle memory into a tiny digital suitcase. You can put that JSON file on a cheap thumb drive, fly across the country, walk into a completely different venue that happens to have a dMix 128 system, load your file into the browser, and instantly, their generic hardware behaves exactly like your custom rig back home.
That portability is revolutionary for touring engineers. You carry your entire complex workflow right in your pocket, not in a massive road case. It completely removes the friction between what you want to hear and the physical actions required to make the system actually produce it.
It really is a masterclass in flexibility. Let's do a quick recap of this journey.
Sounds good.
We started with the sheer impossibility of a zero-install connection. bypassing traditional network bottlenecks by using web MIDI and WebSockets to create a persistent zero-latency pipe right out of a Chrome browser.
Yeah.
We mapped our physical canvas to scale up to 32 faders, safely protected by a duplicate port guard that locks device IDs on load.
Very important step.
Then we explored those shape-shifting VPOTs that use tap commands to speed up line checks, and that brilliant touch-and-turn encoder that bridges the screen and the desk. We tackled complex sends-on fader routing with the safety net of the follow-im digital tether.
Right.
And finally, we looked at how JSON exports allow you to carry your bespoke, custom-mapped workflow anywhere in the world.
It is a comprehensively designed system. It genuinely respects both the immense complexity of the job and the crushing time constraints of the user. But, looking closely at the manual, there's one final feature that really caught my eye.
Oh,
And it has to do with peering behind the curtain of all this technology.
you're talking about debug panel.
I am. The manual notes that if you toggle the debug log open in the browser, you can see every single protocol message and MIDI event happening on the wire.
Like raw data.
Yes. It doesn't hide the mechanics. It shows you the raw data stream of every single button press, every fader move, and every hexadecimal command the app is sending and receiving.
It's literally showing you the matrix of the mixing console.
Exactly.
You're watching the raw code flow by. And this raises a massive question. If you can see all that raw data, if the app is just openly showing you the exact language it uses to talk to the console, what's stopping someone from getting really creative with that?
From a technical standpoint, absolutely nothing.
Nothing at all.
No. If you can read a data stream, you can write to it. An enterprising engineer could take those raw command strings and start reverse engineering them.
Wow.
You could build your own custom macros using third-party scripting software. You could automate complex scene changes based on timecode.
Or even build your own entirely custom hardware. You wouldn't even have to use a standard Mac key controller.
That's true.
If you know the exact MIDI notes and hexadecimal strings the browser expects to see, you could integrate the dMix 128 with totally unconventional homemade MIDI controllers.
Yeah, the possibilities are endless.
You could map the exact values and mix a show with a modified arcade joystick if you wanted to.
I'd love to see that.
It turns a highly professional, pristine mixing console into an absolute hacker's playground.
It really invites the user to push the boundaries of how live sound is fundamentally mixed. It's not a closed proprietary black box. It's an open dialogue between the hardware and the software.
An open dialogue through a simple HTML file. It really brings us right back to that opening thought, doesn't it?
It does.
The sheer paradox of it all. The illusion that a massive, capable, deeply customizable 32-fader control surface inherently requires heavy, permanent, frustrating software. It simply doesn't.
Not anymore.
It just requires you, your browser, and the willingness to explore the mechanics. It leaves you wondering, if all of this power, all this real-time routing and hardware communication can live inside a generic web page, what else in our heavy physical world is just waiting to be replaced by a smart piece of code and a green connected dot? Think about that next time you sit down at a desk. We'll catch you on the next deep dive.